All right, so yesterday we were doing rates of change, which is just the slope. You have two different types. You have the average and you have the instantaneous. Average is the slope of the secant line between 2 points, whereas the instantaneous is the slope of the tangent line at 1 point. The formula for AROC is f of b minus f of a, which is basically the y value at b minus the y value at a all over b minus a. For IROC, the formula is exactly the same, except you have to first convert it into AROC. So yesterday we did a question where they wanted to find the IROC at 15. So you can either go from 14 to 15, called preceding. You can go from 15 to 16. Now this becomes the following, and then you take the average of them. That's one way to do it. Or you can go from 14 to 16. Whatever this number is, it needs to be in the middle. And this is called the centered interval. And this will also give you the answer. Let's see what we can do over here. So here's a question. We have a volume of a cube, and they want the IROC value when the x value is 5. How do we do this? So you can either go do the preceding, following, centered. So here they want to do 5, right? What we need to do is if they want the IROC at 5, that's the same thing as finding the AROC between 4 and 6, because 5 would be exactly in the middle, yeah?
Mm-hmm.
So here what you do is you do f of 6 minus f of 4 all over 6 minus 4. 6 cubed is 216. 4 cubed is 64. Divided by 2. Okay, so it's 216 minus 64 divided by 2. The answer is 76. What would be the units here? So if you graph this, you have some cubic function. What's on the y-axis? What's the y value here? What does v of x represent?
The volume.
So on the y-axis, you have volume, which is measured in cubic centimeters, so cm cubed. What about on the x-axis? What do we have? What does
The
x
side
represent?
line.
Yeah, the side length. So that is in centimeters, right? So the unit here is cm cubed over cm, okay? Like that. Rise over run. This and this cancels out, so you get 76 cm squared as the final answer. And that's one way of doing it. There is a precise answer to this. The exact answer is 75. 76 is good, but we can do better. So now, instead of going from 4 to 6, what we're gonna do is, we're gonna use a centered interval idea, but now we're gonna go from, because right now the difference here is 2, yeah? You see this?
Mm-hmm.
So the lower that difference, the better your answer will be, the more precise it's going to be. So instead of going from 4 to 6, I'm gonna go from 4.99, okay, to well, 4.99 would be the lower bound because it's less than 5. I'm gonna go from 4.99 to 5.01. Why am I doing this? Because now the difference is just 0.02. Last time it was 2, now we've made the difference very small. And that's the idea. The smaller this difference is, the more precise your answer will be. So now if we plug this in, 5.01 cubed minus 4.99 cubed divided by 0.02, that gives me 75.0001 centimeters squared. So that's the idea. You just go up and down. For 5, you go up and down 0.01. That'll give you a pretty good answer. You can also do 0.001, but the smaller that number, the better, more precise your answer will be. Cool?
Mm-hmm.
So the answer here is 75 precisely. I'll show you how to get 75, but this is a pretty good approximation. Just go up and down. Actually, let me just show you right here how to get that 75. So this is again, this is just an approximate. This thing that we did is just an approximate. There is a way to get the precise answer. And this is called the algebraic way. The other ones, this one you need a calculator, the thing we just did, but this one you don't really need a calculator. This is called the difference quotient. It's just a fancy name, but let's say you have, so here v of x is x cubed. What'll be v of 1?
1.
1, right? What about v of a?
A cubed.
What about v of a plus h? You want to replace this x with whatever's in this bracket. So
A plus h cubed.
yeah, so this will be a plus h cubed. Why is this important? Because to use the difference quotient, you need to use this formula right here. So here, f is just a function that's redundant, b of a of s, a plus h, and this is the same thing. We're going to use this formula. So f of a plus h, that will be a plus h cubed in this case, right? Like that. Minus f of a, or the main function here. So that's just a cubed all over h, okay? Like that. I'm just using this formula. What's a plus h cubed? Is it a cubed plus h cubed?
No.
No, it's not. There's more things here. These will be part of it, but there's more things. So how do you open something with the higher power? We're going to use this idea of Pascal's triangle, which is my preferred way. You have 1 here. You have 1 and 1 here. Don't worry too much about it if you don't understand this, but what you do is basically, this is power 0. This level is power 1. This next level will be power 2. There's always going to be 1 in the start and at the end. The middle number will always be the sum. So over here, it'll be 1 plus 1, 2. And then finally, we're interested in x cubed. There's going to be a 1 over here. There's going to be a 1 over here. Now you're going to get 2 numbers in the middle. What's 1 plus 2?
3.
Same thing here. 2 plus 1 is a 3. So this is what we're interested in. Now, how does this help us open this bracket? What this says is these are the coefficients of the terms. There's going to be 4 terms, and these are the coefficients of those terms. The first term will have a coefficient of 1. What you do with this is you take this coefficient, you take your first variable, first letter, and you take it to its maximum power like that. Plus. Now you take your second coefficient, 3. You take your first term, it has a maximum power of 3. This is going to go down by 1. You take your second term, and its power, it didn't exist for the first term, its power is going to go up by 1. And then you keep going. So the next term will be 3. What will be the power of a here? The power of a has been going down.
It'll be 1.
It'll be 1. What will be the power of h?
0.
2. H, 1, 2. The powers in here always adds up to 3, whatever this is. So here they should always add up to 3. So here the power of h will be 2. And then for the last term, the coefficient is 1. Now a is going to disappear. A will be to the power of 0, whereas h will be to the maximum power like that, h3. So that's what you get when you open this bracket using Pascal's triangle. And this is very powerful if you have like x6 or x7 or something like that. Also pretty useful for x3. And then we do minus a cubed all over h. Can I cancel out this and this? There's a minus and one of them is a plus.
No.
Yes, you can. So 1a cubed and minus a cubed is just a 0, so you can cancel them out. So now I'm left with 3a squared h plus 3a h squared plus h cubed all over h. Now the goal here, when you use this method, the goal is to cancel out that h in the denominator, because that h in the denominator is technically 0. Like I said before, you want to reduce, you see this? Last time we had 0.02 difference. The smaller this value is, the more precise your answer will be. So here, h is, it's not 0 technically, it's approaching 0. The limit will be 0, but it's not, it'll never get there. So we need to cancel out this h. That's the main idea. Let me pull out an h in the numerator like this. So then I'll be left with 3a squared plus 3ah plus h squared all over h. Can I cancel out the h's?
Yes.
This is gone. So now remember, h is 0. So if there's any other h's remaining, they will be 0. So you can only do this after you cancel out that h in the denominator. So you have 3ah, this will be 3a times 0, so this is a 0, goes away. H squared is now 0 squared, that goes away. And then that's what you're left with, 3a squared. And this thing right here, this is the IROC function. This you'll get from the main function after doing the difference quotient. Now you just plug this value as a to get the precise answer. That's going to be 3 times 5 squared, 75. That's the precise answer. When we did it, we got 75.0001. That's good enough, but this is a precise answer. And you need to use the difference quotient to do this. And difference quotient will always, you need to cancel out the h. You need to find a way to cancel out that h in the denominator. It's easy for polynomial functions, but if you get something else, then it's slightly trickier. So the last question was a function. They gave us a function, so we knew what the value would be for 4.99 or 5.01 or anything. Here we have a table of values. We don't know what the y value is at 4.99. We do know from 4 to 6, but we don't know for 4.99. So that approach going from 4.99 to 5.01 is not going to work here because we don't know what the y value is for both of these. For this question, if you're given a table of values, the best method is to use centered interval. So they want it at 5. Which one is better, do you think? Do we go from 4 to 5, 5 to 6, or 4 to 6? Which one would be best?
4 to 6.
4 to 6. So this one, you have to use a centered interval from 4 to 6. So the answer to part A will be f of 6 minus f of 4 divided by 6 minus 4. And this will give you the answer at 5. So f of 6 is 310. F of 4 is 250 divided by 2. So that's 30. What's the unit? Look at what your rise and run are. What's our y value? What does it represent?
Temperature.
So we have degree Fahrenheit. What about the X?
Minutes.
So there you go. That's gonna be the units.
Mm-hmm.
And that's the answer to part A. Part B, estimate this using a quadratic model. Okay, how do you do that by hand? I don't think you can do that by hand. Because to use a quadratic model, you need the x-intercept, y-intercept, the vertex, any of these, or all of these, in fact. We do have the y-intercept, but we don't have the vertex. Let me just see what they did, because I don't think this is doable by hand. Yeah, so this is a graphing calculator problem, figures, because this could be the vertex, but 11 could be 420. We don't know that. Or 11 could be 380. We don't know. We don't have enough information to do this by hand. But let me show you how to do this using technology. Sometimes that's the only thing that's going to work. So what we do is I'm going to plug these numbers in. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to plug the y values as well. This is the only way to get an equation out of this. I guess if you really wanted to, you could force a quadratic, but 360, 380, 400. So I've typed in the values on Excel. What you do is then you're gonna highlight those values, everything that you just typed in. Gonna go to insert, gonna go to charts, gonna go to scatter plot. Do you see that? And that's our quadratic. And then we're gonna click this, right click it, add a trend line. Now this is a linear trend line. It wants us to do a quadratic. So I'm going to look over here. Quadratic is not an exponential, it's a polynomial. What's the order of a quadratic function? Order just means the power. It'll be 2, yeah?
Mm-hmm.
If you want a cubic function, you go order 3. If you want a quartic or x4, you go order 4. But here we're going to stick with order 2. Gonna go down here, and this is what we need. Display the equation. And boom, that's our quadratic model right there. That makes sense?
Mm-hmm.
That's our function, and that's how to get this. Um, What's funny is that even though we have the y-intercept here, this doesn't fit the model well enough for it to be the y-intercept. The y-intercept is actually 74. Now, how is that possible? It's because what we did was we had this in as a data point, but then we have these. When you connect the dots, it doesn't mean it's gonna fit exactly, okay? It might go over here, it might go over here, whichever the Excel thinks is better. How does it determine what's better? It uses something called the r² value. If you go down here, right below the equation, there's something called r². The closer this number is to 1, the better the model is, okay? So now if I actually, let me see if it'll let me do this. Yeah, so right here, set intercept, yeah, you see this, set intercept?
Mm-hmm.
This is the y-intercept. If I put this as 70, I'm predicting this r² value will go down. So now let's fit this 70. You see it went down by 0.0001, which is not a super big deal. But the higher it is, the better the model is. So that's why it went with 74. In fact, you can actually make this even better by testing the different orders here. So we had order 2. Let's try cubic. See, it's even better now. That r² value went up, yeah? Will it ever become 1? I don't think it's ever going to become exactly 1. So Anyways, for our purposes, it's going to be a quadratic model. And that's the equation right there. This is the equation. So now what we do is we're going to do the same thing, and let's say what we get. I'm going to do, this is for part B. I'm going to do f of 5.01. I'm going to go down, up by 0.01. Then I'm going to go down by 0.01. This is the best method if you have an equation. Like that, and let me just plug this in and let's see what we get. There's no way this is doable by hand. Squared plus 50.455 times 5.01 plus 74.091. So I get some number here, 281, and then minus negative 1.8182 times 4.99 squared plus 50.45, 4.99 plus 74.091 times 4.99 divided by 0.02. Don't know if I plugged it in right, but this gives me a weird value, negative 14,748.88. Don't think I plugged it in right. Yeah, no, I did not. But they got the same equation. See over here? I don't know how they got. They used TI-84, the calculator. This and this is pretty much the same thing. If I had plugged it in right, going from 4.99 to 5.01, I would have gotten 32. And 32 is the best answer for this question. Using, I don't know if it's the best, but it's definitely better than going from 4 to 6, because the difference here in the denominator is 2. You want to make the difference very small. This is a good difference, 0.02. So that's how you can model something on Excel and use it to answer questions, because not everything will be doable by hand. Okay, let's look at raccoons. We're given an equation for their population, and T is months. Okay, part A, determine the population at 2.5. Now it's asking you to find the population, not rate of change or anything. How do you do part A?
You plug in 2.5 ST.
So 100 plus 30, 100 plus 30 plus, or 30 times 2.5 plus 4 times 2.5 squared. I get 200. Nice even number, 200. Part B, determine the average rate of change from 0 to 2.5 months. Now what do we do? It's asking us to find the average rate of change, which is the slope of the secant line. You just use the formula for part B. We're just gonna do f of b, so f of 2.5 minus f of 0 all over 2.5 minus 0. If they give you two different values, or if they give you an interval, that's probably going to be an AROC question, which it is. You just use this formula. Okay? It's not super difficult. So you just plug everything in now. So 100 plus 30 times 2.5 plus 4 times 2.5 squared minus 100 divided by 2.5. The answer is 40. What's the unit? Look at what y and x represents in this question. On the y-axis, we have the number of raccoons, right? So their population is a unit, number of raccoons. What about the denominator?
Months.
Months, yeah. So between 0 and 2.5 months, their population was increasing by 40 per month, okay? What about part C now? Part C is asking us for 2.5 months. Instantaneous. You know it's instantaneous because you only have one x value. But because of this word here, exactly also means instantaneous at that very specific time. What's the approach for C? It's the same formula, right? It's f of something minus f of something all over something minus something. But it's not 2.5 and 0. You want to go up, yeah? You
Mhm.
want to go up by 0.01 and you want to go down. If you go down by 0.01, what do you get? 2.5 minus 0.01. It'll be 2.49. Just up one, down one, okay? Same thing in the denominator, like that. And that will give you the instantaneous. IROC is basically just AROC, but your X value, you just want to go up and down by 0.01. So here, let me plug this in. So we have 100 plus 30 times 2.51 plus 4 times 2.51 squared minus 100 plus 30 times 2.49 plus 4 times 2.49 squared divided by 0.02. I get a 50. 50 raccoons per month. That makes sense?
Mhm.
That's all you have to do. It's like 2 steps. It's just a calculator. You just want to plug this as t and then take away this as t. What's the answer to part D? Explain why your answers are different from A, B, and C. The answer to A was 200, B was 40, and C was 50. Why are they different? Well, it's because part A is asking us for the population, not for the rate of change, right?
Mhm.
So it's going to be different. The unit for part A is just raccoons, whereas B is asking us for the rate of change, the average rate of change from 0 to 2.5. It's asking us for the slope of the secant line between the 0 and 2.5. And C is asking us to find the slope of the tangent line, which is 50. That's why they're different, because it's asking us for 3 different things. They don't all have to be the same. Kind of make sense? If you want another overview of what just happened, this is a quadratic, it's opening up. I don't think there will be an x-intercept. Actually, we can quickly check if there will be an x-intercept by doing this. This comes from the quadratic formula. If that number is negative, it won't have a x-intercepts. Yeah, it's negative 700, so it definitely doesn't have an x-intercept. So the graph of this would look probably something like this. We can find where the vertex is. Even though it doesn't have an x-intercept, it's always going to have a vertex or a turning point quadratic. It's at minus b over 2a. So here it'll be minus 30 over 200, which is what, 3 over 20? What's 3 over 20? 0.15, I think. Negative 3 divided by 20. Yeah, so that's a negative number. So our vertex will be actually somewhere over here. And the y-intercept is 100. So that's the sketch, okay? Part A, what did we find? It asked us to find the population at 2.5. So for part A, what we found was the y value when the x value was 2.5. Part B, what we did was we found the slope of the secant line. We found the slope of this line that goes from a 0 to 2.5. Whereas for part C, we found the slope of the tangent line that's perpendicular at this point. So we're finding 3 different things. That's why there's 3 different answers. Okay, one last thing. Let's see if this is the precise answer. I think 50 is the precise answer. We can double check this. And this is going to be the hardest thing. We did it before, but this is definitely going to be the hardest thing. So now, so that's called, when you do plus minus 0.01, this is the calculator approach. It'll give you a pretty good answer, but may not be the precise answer. To get the precise answer, you have to use the difference quotient. The difference quotient says f of a plus h minus f of a all over h. You need to first cancel out that h in the denominator, and then you need to plug everything else as every other h as 0, and then finally you plug in the x value, and that'll give you the answer. That'll give you the instantaneous rate of change. So difference quotient is for instantaneous rate of change. So here, this will be slightly tricky. If P of t is 100 plus 30t plus 4t squared, what's P of a plus h? You want to replace all the t's that you have with a plus h. You see this, there's a t here and here.
Mm-hmm.
Just replace that with a plus h. It's going to become 100 plus 30 times what? So replace this with a plus h, like that. And then plus 4 times what?
A plus h squared.
Right, so there you go. That's f of a plus h. Minus f of a, so minus the original thing. Whenever you're subtracting something, make sure you have a bracket here. So minus 100 plus 30t minus, or sorry, plus, it'll eventually become minus, but right now it's plus, all over h. Now let's open the brackets. So we have 100 plus 30a plus 30h plus 4a squared. If you open that bracket, 8ah plus 4h squared minus 100 minus 30t minus 4t squared all over h. Can I cancel out the hundreds?
Yes.
What about the 30? Why do I have a and why do I have t? So this should have been a, which means these are a's as well. Okay, what about the 30a? This and this, can I cancel them out?
Yes.
What about the 4a squared?
Mm-hmm.
So that's always what's going to happen. Whenever you open the bracket using the difference quotient, half the things are always going to cancel out. Whatever's left, you can usually, this always happens to polynomial. For polynomials, you can always pull out an h, and that's the h that's going to cancel out with the denominator. So I have 3 terms left. I'm going to pull out an h from all of them. So h 30 plus 8a plus 4h. And now this is going to cancel out with the h in the denominator. And now if there's any other h remaining, there is one here, that's going to be a 0, so you can ignore this. So 30 plus 8a, this is your IROC function. Now, so we're on this step. Now for the final step, we're going to plug in that value of 2.5. So 30 plus 8 times 2.5. 30 plus 8 times 2.5, that's 50. Exactly 50, and that's the precise answer. That's also what we got before using the calculator approach. But this is the more precise. Well, they ended up being the same, but this method will always give you a more precise answer. Now, difference quotient is the long way of doing things. It's the long way of finding the IROC function, the instantaneous rate of change function. Let me show you an easier way of getting this exact same answer. It's going to be a 2 steps. We're gonna get 30 plus 8a or 8t or whatever. Now this is a short way. You take your function. This is p of t. The IROC function is called p prime of t. P prime of t, like that. If you have a number, you see this? It completely disappears. So the 100 is gone. Now you move on to the next term.
Mhm.
This is a polynomial. What happens is, what's the power of t right now?
It's 1.
It's 1. That power is going to drop down. It's going to multiply with the number in front of. And then you take away that power. You reduce it by 1. You don't take it away, but you reduce it by 1. So then you would be left with t of 0. You do the same thing over here. You see this 2? It's going to
Mhm.
drop down here. So it becomes 2 times 4, kind of like logs. It's going to drop down here. Now what's going to be the power of t? If you reduce it by 1,
It's 1.
it's 1, right? What's t to the power of 0?
1.
Yeah, so 1 times 30 times 1 is just a 30. And over here we have 8t. Look at this. This is the exact same thing as this. With this one, we had to do the difference quotient. This one, we can just use a shortcut. It's because the shortcut doesn't work for anything that's not a polynomial. That's the issue. That's why you have to do it the long way. Like over here, let's just use the shortcut because why not? It's very powerful in a question like this. Instead of doing like this 4 different times, we can finish this question in 30 seconds. F of x is 6x squared minus 4. What will be f prime of x? You want to bring this number down, right? And take 1 away from it. What do you get? So 2 comes in the front. What's going to be the power of x?
1.
1. So the IROC function is 12x. So to answer these questions, you just plug that as your x value. So the first one will be 12 times negative 2, negative 24. For b, it'll be 12 times 0, 0. So that means at 0, there's a turning point. Because if the slope is 0, that means it's horizontal. The only way that's possible for a quadratic is if there's a turning point. So at 0, there's a turning point or the vertex. What's the answer to C?
Mm,
This is our IROC function. This is the x value. Multiply them.
48.
Yeah, and then for the last one, it's just 12 times 8. What's 12 times 8? It's 96, and there you go. But the issue with this is you can't do this in this course, whatever this course is, you can't use a shortcut. The way you answer this in an assignment or a test is you can either go from, you have to do this 4 different times. You do this approach for A, and then you do the same thing for B, where you'll go from negative 0.01 to positive 0.01. You'll use the calculator approach, or you need to use the difference quotient to show where you got this from. This, you'll get the same thing. You'll get 12a if you use the formula for difference quotient. That makes sense? So you'd have to do it the long way. Here, we just kind of cheated a little bit, but I always like to be efficient. I don't know why the course doesn't allow you to be, but it is what it is. Like I said, it's because the shortcut doesn't work for anything that's not a polynomial. That's why difference quotient is the way to go. Now let's see this. This is what I'm talking about here. What function do we have? What kind of a function do we have here? Is it a quadratic? It is not, right? You see h of t there? It is a exponential. So your shortcut is not going to work because now if you do, this number has to be a whole number, not a variable. You can't just bring that down and take it away from one. That's not going to work for exponentials. That's only for polynomial functions. So here we have to do it the calculator approach. What's the x value? It's asking us for the instantaneous rate of change for what year? It's right here. At 8, so t equals 8. It's asking us to find t equals 8, the IROC. So f of something minus f of something it'll be. What are these numbers? You want to go up by 0.01 and you want to go down by 0.01, like that. Let's plug this in. So it'll be 125,000 times 1.06 to the power of 8.01 minus the same thing times 1.06 to the power of 7.99 divided by 0.02. I get 11,608.79. What's the unit?
The value of the home over the number of years.
So it'll be dollars per year, okay? Dollars per year. And that's it for this question. Actually, when I said there's no shortcut, I lied. It's not the same idea as the polynomial one. There is a way to get h prime of t. Let me show you. What you do is h prime of t, funnily enough, is the exact same thing as the main function. This is only for this. This is a shortcut for exponentials. Last time we had the shortcut for polynomial. This is a shortcut for exponentials. It's gonna be the exact same thing that we had before, like that. But you multiply this with the ln of the base, the ln of this. And that's the IROC function basically. Let me plug 8 in here and let's see if we get a different answer. I'm predicting we will get a different answer. So I'm just plugging 8 as t here. So this was the answer from the calculator approach. There's something wrong with my thing. Let me just plug this in. So 125,000 times 1.06 to the power of 8 times ln of 1.06. I got 11,608.97. 0.97. Come on, work with me. So it's not a big deal. I mean, the difference is like 0.2-ish, but this is the more precise answer compared to the calculator approach. Did that make sense? So we have a shortcut for basically every type of function. The shortcuts are going to be different and they get more and more complicated, but that's the idea. Work with me. Okay, hopefully it's fixed. All right. Let's go here. You see this is an exponential function? The shortcut for this is going to be that thing times the ln of the base. So it'll be times the ln of whatever this is. What else can we do? What about this one? How would you do this? It's just asking to find the slope of the red line. You just do rise over run for this. It's a one-step answer. What's the slope of the red line? Here, let me draw you the triangle. Run is 1 unit. What's the how many units for the rise?
2.
2. So what's the slope?
2/1. So
Yeah,
it's
it's just
2.
2. It's just 2. That's it, and you're done. Easy peasy. So here we're given a equation f of x. What is going to be f prime of x? Let's use the shortcut. It's a polynomial function. Remember, you need to bring this down, right? You see this too? Bring it down, multiply with the number in front of it, take 1 away from it. So it'll be x power 1. What about the next term? It'll simply be 5. Or if you want the proof, you bring that 1 down, multiply with 5, and you take away power. It's going to become x0. Therefore, the IROC function is x plus 5. That's it. Now look at how easy this becomes. For a, the answer is -5. You just plug that as x. So it's -5 plus 5, it's a 0. For b, it's -5 plus 1, it's -4. For c, it's 5. And for d, it's going to be 8. That is it. Okay? For polynomials, it's super simple. Like, I enjoy doing this for polynomials. For other functions, like, it is going to be slightly different depending on what's going on. Yeah, that's the idea behind rate of change. I actually have to leave a little bit early today, so let's call it there. We can do 10 minutes more next time we meet.
Okay, thank you.
All right, see ya.